We will have today the presentation by Joseph Zhang from Virginia Institute of Marine Science on improving Tide-Estuary representation in MPAS-Ocean.
Okay, thank you, Dorothy. Thank you, everybody, for attending. So this is more or less a progress report, and end of the presentation, we'll also discuss a little bit about the plan for year 3. So this is a joint project between us and Virginia Institute of Marine Science and FHS Group and the University of Maine. So I'll first review what we proposed in the proposal, and also the timeline, so where we are right now. So I will tell you briefly about progress we made in developing the new nearshore component for MPAS, the global MPAS-Ocean model, which we call MPAS-Ol. I stands for implicit. I will tell you about the ongoing work about model coupling to couple this MPAS-Ol to MPAS-Ol. And also, as we promised in the proposal, we also will try to couple another nearshore model called SCHISM to MPAS-Ol. So eventually, so you will have 2 model coupled to the global MPAS-Ocean. So I will tell you a little bit about what the SCHISM model is about and its main features as well. So here's what we all the tasks we proposed. Okay, so it's 15 of them. First 10 tasks are related to hydrodynamics, and the last 5 are related to the biogeochemistry. So I'm very pleased to report that we are making a lot of progress for the 15 tasks. So right now, the first 8 tasks are finished, and the tasks 11, 12, and 13 related to biogeochemistry. So the remaining task is mostly related to the model coupling and the validation of the fully coupled global model and the nearshore model. So MPAS-Ol was proposed to be a nearshore component of global MPAS-Ocean model. So in order to bridge the gap between the global ocean and estuary and the rivers. And the formulation MPAS-Ol is mostly based on the untrimmed 2 formulation. Okay, so it uses finite volume solver, so that's something consistent with the MPAS-Ocean. And the MPAS-Ol uses MPAS approach to reconstruct the tangential velocity using the Stillborn approach. So in order to better conserve the energy and the potential vorticity. So that's something we did differently from untrimmed. But the dynamic core is essentially a semi-implicit nonlinear solver for fully coupled continuity and the momentum equations on orthogonal grids. Okay, so the dynamic core has the following nice properties. Okay, so first of all, the convergence of the nonlinear solver is always guaranteed. So that's nice. And we can do mass conservative wetting and drying with arbitrary time steps and with the positivity enforced. That means you don't get a second step. Okay. And one of the key characteristics of MPAS-Ol is that it allows this subgrid representation of high resolution bathymetry, for example, as it measured in LiDAR. So if you look at the right-hand side, this is a grid we use for Hurricane Sandy study for the lower Manhattan area. So the thick boxes represent the base grid. Okay, so it's relatively coarse with a resolution about 200 meters. So we further subdivide each base grid cell into subgrid. So the subgrid, you probably cannot see very well, but each subgrid cell will have 5-meter resolution. So that's very sufficiently fine enough to represent the LiDAR bathymetry. So this, if you only use the base grid resolution, so the bottom representation is not great, but once you refine to subgrid level, the bottom representation is very good. So we have lots of success stories for applying MPAS-Ol to storm surge related applications. So basically enables us to do very fast and accurate prediction of street level and building level inundations. I'll show you an example later. So one thing I want to emphasize is that because the finite volume solver used inside MPAS-Ol, the grid quality is a key issue. So I will elaborate a little bit more next couple slides. But I'll go very quickly about the numerical algorithm used by MPAS-Ol. So you take any control the finite volume. Okay, so each cell can be only of any polygonal shape. Okay, so I'm using the quads here to just for illustration, but the code can handle any polygonal cell. Okay, so the thick line represents the base grade, and the subgrade, you can now see the subgrade. Okay, this is the thin line here. So the normal velocities are defined and the subside, okay, for subside of each subgrade on the boundary. So that we fully utilize the subgrade information. So the depths are defined at each subgrade level. So we solve the fully coupled continuity and the momentum equation. So we treat all the terms that place stringent numerical stability implicitly. So that include the pressure and the divergence terms, all those, and we group other terms that will be treated explicitly into one term, F here. And we use the coordinates in the vertical. So we had some debate about what kind of vertical coordinates we should use. Because the finite volume framework we used in MPAS-Ol, it's not easy to implement terrain following or generalized terrain following coordinates because you don't have a continuous representation of the bottom. So we use the coordinates in the vertical. And this is a discretized momentum equation and subside level, okay? And this is a matrix form. And then you use finite volume discretization to treat the continuity equation for each cell. This is a cell and base grade level, okay? So V means the volume, okay? Volume of each base grade cell. And this term is nothing but the summation of all the fluxes from the subsides, right? So definition of the volume is given here. So as you can see, we guarantee the positivity. So, there's no negative depth here. So, and also we can do partial wetting and drying because everything is defined. The integration is carried out through all the subcells. So some cells maybe some subgrade cell may be wet, but other subgrade cell may be dry. So we allow partial wetting and drying this way. And after you substitute the momentum equation into continuity equation, you get one equation for the unknown elevations, which is a weakly nonlinear equation for the elevation because the volume and next time level is a function of the free surface elevation. And you can mathematically prove that if you use Newton iteration method, the convergence is guaranteed. Okay, and in practice, usually very fast. Guaranteed, usually converge within 10 iterations. And so the scheme basically enforces strict positivity and mass conservation, and allows partial wetting and drying inundation process under any time step. So you get both accuracy and efficiency this way. So it's great for storm surge applications. So here's a little bit detail about how we treat the subgrade bathymetry for two types of cells, quad. That's relatively simple. You just subdivide each rectangles into smaller rectangles, right? For triangle, we use a Pascal diagram to subdivide each triangle into smaller triangles. So we could, in theory, do this kind of a subgrade discretization for any cells of any types of polygon, but we haven't done that mostly because we found that it's really difficult to generate good quality orthogonal grids using other types of polygons. But in theory, this can be done. Okay. So I will not go into detail about the tracer transport algorithm because they are exactly the same. as the finite volume solver inside the SCHISM. So, and we have lots of publications to prove that this is great for cross-scale type of applications because it's accurate and also very efficient. It's implicit in the vertical, for example. So I would directly jump into the benchmark. The first benchmark we did is nonlinear inundation problem, for which we do have analytical solutions. So it's a classical case for parabolic bow with initial displacement of free surface, so represented by the thin blue line here. So all boundaries are closed, so the volume should be conserved, and so is the energy. Okay, so you can also use this to test the energy conservation as well. So we use low bottom friction, low dissipation, and we use Kazuli's configuration. And so the parameters are shown here. And we use uniform quad, like a structure grid, but we rotate it to an angle, so to just test out the radial symmetry. And we use a relatively coarse resolution, 2 kilometer, right? So 1 vertical level, and the time step you can see here is very large, 6 minutes, okay, for strong gradient drawing. So that's relatively rare. And we did lots of sensitivity tests as well. So first of all, this is the animation shows the instantaneous position of the inundation line. You can see it's radially symmetric, so we don't have lots of wiggles, so that's a good thing. And on the right, this is a time series of total volume inside the domain. So the volume should be strictly conserved. As you can see that the models conserve the volume within machine precision, so which is a very good thing. So we also look at the time series comparisons and 4 stations. One of them is always wet, and other 3 stations are located near the maximum inundation extent. So it's in a wetting and drying zone. Okay. And here are the comparison for elevations for the 4 stations. And you can see that the results are quite satisfactory given the fact that we are really using a coarse grade for coarse baseline grade, 2 kilometer resolutions. So this is quite good. And the model runs very fast as well. So we also apply this to a number of hurricane storm surge type of study. So I'm going to show you the results for the 2012 Hurricane Sandy for New York City and Long Island Sound. So the model grade covers relatively large extent, okay, both New York City and Long Island Sound. So we use a structure grid, okay, and the base grade resolution is about 200 meters. So again, relatively coarse. And the total number of elements and the base grade level is about 90,000. But we use a subgrade resolution 5 meters, so we can take advantage of the 5-meter resolution LiDAR DEM we got for New York City. And we tried 2 types of open boundary condition, one from observed water level, another one from results from large-scale SCHISM model. So the results are quite comparable, which is quite reassuring. And we use time step. In this case, we use time step of 3 minutes, so still quite large. 80 Intel cores, we get a speed up of about 720 than real time. So in comparison, for the same grade, untrimmed 2 will be about 18 times slower because untrimmed 2 has not been paralyzed. So the efficiency is quite good for this kind of high resolution inundation studies. So here are some comparison for both the total water level on the left and the surge on the right. So it's decided and the pinch point. So you can see the model skills is really good. And the table here shows all the error matrix. So the errors on the order of 10 centimeters root mean square. So that's pretty good. Okay. And we also look at the inundation extent comparison. Okay. We compare with the high resolution street level FEMA map, inundation map. Okay. So this is shown on the top right. this is a FEMA estimated inundation extent, whereas this is a model predicted. So you can see that the model is doing pretty good job in terms of capturing some very detailed street level inundations. So overall, in the entire domain for the New Jersey and New York region, the modeled inundation matches approximately 75% with the FEMA map. So that's very good. And the average error for the high water mark is on the order of 10 centimeters. That's again quite good. Okay. So we also apply this MPAS-Ol in a 3D baroclinic mode to some estuaries. So I'm going to show you the results for the San Francisco Bay. So in this case, we just cut off the domain and to include only the Bay only. So we did not include the San Francisco Bay, the Delta region, so because it's too complex. And we have lots of experience with this domain, including using the SCHISM model. So even this is a relatively simple geometry, really, compared to other estuaries, but we had some challenges. The student actually spent lots of time generating the grid, orthogonal grid using the commercial software called Janet. We have also tried Jigsaw, and Janet is better because it allows us more freedom to resolve the key features such as channel lines. Okay, but each grid really took about 1 week, so it's quite time consuming even for this kind of relatively simple geometry. So I'm showing you two versions of the grid. Okay, one, the coarser grid uses about 400 meter resolution near the channel, and the final one is about twice as fine. So, and the 3-minute time step, and in the vertical we use 1 meter near the surface, and we had some problem with the silver approach near the land boundary, and later on we found out that this approach basically is a way to reconstruct tangential velocity from a normal velocity. It's highly sensitive to grid quality, okay, and the grid quality unfortunately cannot be very good near the boundary, okay, no matter how you tune the grid. So later on we just relax this approach near the land boundary to get rid of this problem. And we also tried a very simple averaging approach, to interpolate normal velocity, to interpolate the tangential velocity from normal velocity. So this approach, the results give more or less the same results as the super approach for this test case and other test cases. So that's the indication that really energy conservation is not really a major issue in estuary and nearshore system, because the system itself has enough new physical dissipations inside already. So here are some comparisons for elevations and 5 stations inside the bay. So in general, they are satisfactory. The tide range is slightly overestimated. And here are the comparison for the salinity. So we captured the average quite well, but the variability is a little bit underestimated. So the results is worse than the SCHISM results, which is not really surprising because this is a new model, so it needs more time to mature. So we also tested the model sensitivity to number of subgrades we use. Okay, so this diagram shows the elevation at one particular station using 1 node subdivision and 3 subdivisions within each base grade cell. So you can see some difference even at the elevation level. Okay, so what this says is that the tides are sensitive to the volume, because once you subdivide each grade into subgrade, the grade will see slightly different bathymetry, right? As I showed before. So your volume may be slightly off. So this is good news for elevation, because by subdividing grade cell, you can improve the elevation. But unfortunately, this does not help the 3D velocity and tracer transport. So it's a bit disappointing. We were hoping that we can just use a uniform structure grade with subgrade enabled do this kind of field scale applications, but it turned out it's not really possible. And so this goes back to the grade qualities. That means you still have to pay attention to the grade generation for unstructured grade, unstructured grade, orthogonal grade. And our experiences and grade quality is very, very important for the calibration process, and it's a highly non-trivial exercise. So one of the problems with orthogonal grade generation is that it's a non-local process. That means you cannot calibrate the model on a regional basis as we did for SCHISM. Okay. So for example, we know this is Aquinas Strait, which is shown here. Okay, so this strait is a key choke point for this base system, and we want to edit the grade here. Okay, you can see that the grade, although the grade is orthogonal, the resolution is not optimal because this region you have too much resolution, and here you don't have enough resolution. So we try to edit this, but by doing so, you have to change the grade in other regions. So you can change the results in other regions. So this becomes a global exercise, which is quite time-consuming. So another issue, which is well known with this type of finite volume model, is that you only compute the normal velocity, and the tangential velocity is actually interpreted from normal velocity. So as a result, you are essentially only driving the flow along the normal velocity. You're giving the model the preferred direction. But for S-stream processes, for many processes will have a preferred direction, right? For example, channelized flow, you should follow the channel. So if you don't really align your grade with the channel lines, you may have too much wave reflection. Okay, so this is very different from finite element formulations in SCHISM, where we do not have any preferred direction. So the tangential component and the normal component are treated equally. So that's the key difference. So anyway, so this brings me to the second S-stream model. So SCHISM has been there for almost 20 years now, and it's well recognized now, and we have built a modeling system around it, and it has been extensively applied to estuaries and regional oceans worldwide. And the recently one developer group has added ESMF coupler to the modeling system. So the modeling system can be coupled to any other models that have ESMF coupler. So one key difference between the SCHISM and other types of model is that it uses a finite element, as I said, okay, to solve the coupled continuity and moment equation. So that's the key difference. So SCHISM is quite unique in a number of aspects, okay, when you compare to peer models. Number one, it does not smooth any grade, okay, it does not smooth the bathymetry. So we really put lots of effort to really faithfully represent the underlying bathymetry, okay, nearshore. And you can see, read our recent modeling paper, and just came out, where we demonstrated how important the representation of bathymetry is for the nearshore estuaries. And this becomes a lot harder when you try to apply high resolution, okay, but even with a very high resolution, we do not smooth the bathymetry. The second one is we use implicit and finite elements. So as a result, the model is very tolerant of bad quality mesh, at least in the nearshore regimes. So the accuracy of the SCHISM is ensured through a balance between the numerical diffusion and numerical dispersion. Okay, and the efficiency is guaranteed through this flexible 3D grading system. So we call it polymorphism. Okay, I will say a little bit more in the next couple of slides. So as a result, you can use one single grade, SCHISM grade, to cover from deep ocean all the way to mountain creeks. Okay, I'll show you some example later. So the model has been well benchmarked, and the inundation schemes has been certified by tsunami program for inundation processes. And the whole modeling system has been parallelized using a MPI plus OpenMP, so it's hybrid parallel paradigm. Okay, and the strong scaling is good through the bathymetry solver, and the model has been operational tested by a number of government agencies. So recently, EU organizations starting to apply this for European seas as well. So I'd like to elaborate a little bit more about some key features in SCHISM. Okay, just give you some idea how we do estuary and nearshore systems. The first one is what we call the resolution on demand. So, for example, in this particular case, we use relatively coarse grid inside the coastal ocean, and we find into the bays and estuaries. And when we reach the region of interest, okay, which in this case is the marsh, lots of fringing marshes along the tributaries. We really just put lots of resolution. We jack up the resolution very fast and very fine. So if you look at each box and represent marsh, the coast shore resolution is 1 meter, and the long shore is 10 meter. Okay, and in this case, we are interested in the impact of bridge pilings on the water quality in the lower James River. So this bridge crossing happened to occur near the where the salt intrusion occurs. Okay, but even with that, we are able to use 3D model and refine to the bridge piling level, which each bridge piling has a diameter about 1 to 2 meters. Okay, so we can jack up the resolution very fast, and the total number of bridge piling in this case about 2,000. Okay, so so the implicit finite element formulation inside SCHISM really makes it very tolerant of this kind of band meshes. And on the other hand, if the model cannot tolerate this, if you insist on this kind of smooth grade, good quality grade, we did an estimation. Okay, so the grade size will become prohibitively large. Okay, for example, more than 10 times larger. Okay, so the SCHISM's secure stability and robustness really allows user to apply high resolution and any region almost at will. Okay, so this is quite unique. The second capability is what we call quick to ocean capability. So, and the underlying enabler for this kind of capability is the polymorphism. So we can basically blend 3D cell, 2D cell, and quasi 1D cells in a single SCHISM grid. Okay, seamlessly welded into each single grid. Okay, so this is very, very good for both accuracy and efficiency. So as you can imagine, if you want to couple coastal oceans with mountain rivers, you need this kind of capabilities. As a matter of fact, we are working with NOAA in an integrated water project to use this kind of quick to ocean capabilities to link oceanic processes to national water model, which covers the mountain rivers. So in this type of applications, we typically use very high resolutions in estuaries and upstream rivers down to a couple meters. Okay, but we can still use large time step because the model is stable, implicit. So typically we use 2-minute time step, non-split. There's no mode splitting. And the model can easily represent the complex features in estuaries and rivers using skew elements. And added bonus is that the vegetation effects have been incorporated into the model implicitly. That means you do not have to reduce the time step, even with the presence of vegetation. So this is a very good feature, and they are for water quality studies. For example, we are working with EPA and the California Department of Water Resource for this type of water quality related studies in bays and estuaries. And we can easily link this model to land model or watershed models. So I apologize, I probably have to put this here. So here is the application case that picked NOAA's interest originally. So you can see, and we are able to use very high resolution to represent the Delta region, right? And go very upstream for the San Clemente River and the San Joaquin rivers. So this is what we call creek-to-ocean capability. So the flexible gradient system inside the SCHISM also allows it to very accurately capture the bottom controlled processes because we use shave sail near the bottom. So here's an example of this type of bottom controlled processes in the form of a gravity flow. Okay, there's a very strong gravity flow across the Bosphorus Strait into the canyons of Black Sea. Okay, so as you can imagine, this is a very challenging case. So you can see the gravity flow, shooting down the steep slope here, and you can see from here as well. Okay, so this is the plan view of the bottom salinity. Okay, you can see the intrusion path, the seniors, because we have multiple seals, and eventually this is a canyon line. Okay, you overshoot into the canyon. So, but the Black Sea itself is kind of strange. It's semi-enclosed, so it only exchange waters through the Bosphorus Strait with the Atlantic Ocean. But the inside this Black Sea, this stratification is very, very strong. It's very stable. So if you want to do long-term study, you want to maintain that very strong stratification, in the same time allow this kind of disturbance propagating from Bosphorus Strait to reach Black Sea. Okay, so it's a challenging problem, but because of the particular vertical gradient system we use, we are able to accurately capture this kind of processes, including the interleaving process, multi-layer structure for temperature and salinity, so which are observed in the field. And those processes are important because they serve as one of the few mechanisms for relating the oxygen into the near the inside the Black Sea. So lastly, I'd like to talk about ongoing work of coupling the MPAS-Ol and the SCHISM into the MPAS-Ol. Okay, so we promised we're going to publish 2 models into the global ocean model, MPAS-Ol. So after some thought, we came up with this relatively simple relaxation method. I think it will work. I will show you the detail in the next slides. But essentially, we overlap the MPAS grid with the nearshore model grid. Okay, so the thick black line here represents the MPAS boundary of MPAS-Ol, and the dashed line represents the nearshore model boundary. Okay, so the overlap in this region. So the idea is to relax the state variables of the 2 models to each other. Okay. But after discussing this idea with you guys, we found that the existing E3SM coupler design is not appropriate for this type of coupling, so we have to do it ourselves. Unfortunately, ESMF component is not inside the MPAS-Ol, so we cannot use that. So, so in terms of actual coupling strategy, okay, so we basically advance MPAS-Ol from one time step to another. Okay, say T1 to T2, and then we send the information at T1 and T2 to SCHISM. Okay, and then SCHISM will take this information and advance the same amount of time, but use the elevation and velocity information from MPAS-Ol as boundary condition and this boundary. Okay, and we do linear interpolation in time, and for tracer concentrations, SCHISM will relax to a tracer concentration in a overlapping zone to the MPAS-Ocean. Then at the end of the time stepping, SCHISM will send back the information in the overlapping zone to MPAS-Ol and the T2, and then MPAS-Ol will in turn relax all variables, including elevation and velocity in the overlapping zone. Okay, so this is essentially a predictor-corrector approach, and then MPAS-Ol will continue the time stepping, and the process will be repeated. So I think this approach should work with tides as well eventually, but MPAS-Ol will need to use a smaller time step. So we can discuss the strategy during the discussion time. So instead of going through this detailed mechanism of coupling, so I propose what time is it now? So, yeah, I propose I directly go to summary. Okay, so and we come back to the detailed coupling strategy. So we have implemented a new nearshore component for MPAS-Ol. We call it MPAS-Ol, based on the finite difference approach on orthogonal grids with arbitrary polygonal type, and we use implicit time stepping to avoid the stability constraint, and we use subgrid and robust nonlinear solver for mass conservative wetting and drying. So this is demonstrated to be very good for storm surge applications. And the 3D results are reasonable. That's all I have to say. Really, it's definitely worse than SCHISM, but that's probably expected. But probably more disturbing is the fact that the model really requires a very good high quality mesh, okay, for orthogonal grids. So this is challenging with the current set of tools. I had a talk with Darren in Degra, and the conference last month in Europe. He's a developer of Jigsaw, so he's interested in helping us basically streamline the grid generation processes. But in our experience, it's a hard problem. So I didn't cover in this talk the progress on biogeochemistry, but Zhang would present the result at the November meeting. So in short, we have also made progress in that front, including a new carbon module and sediment transport and a new treatment for light. And we are working on the coupling. So with that, maybe we can go into the discussion section. Dorothy?
Yes, this is Dorothy. I think what we want to do, we could probably take a couple minutes for general questions from the whole group, and then after 5 minutes or so, I think we want to go into a smaller group and have a more detailed question about the plans with respect to E3SM for the science and technical aspects. But are there any questions from this group for Joseph?
This is Mark Peterson, and Joseph, thanks for the nice summary. So overall, would you say that there's advantages to MPAS-Ol, or what were the expected advantages to going to a tris grid, and have any of those been realized?
What's the advantage of MPAS-Ol using tricks?
I'm just saying, what's the advantage over SCHISM? Were we trying out a new numerical method just to test it?
Yeah, currently my answer is not much. Okay, so like I said, it's a relatively new model, but there are some issues we have to overcome to think harder. But originally we proposed this model mostly because we thought MPAS-Ol using the finite volume type approach, so it's more natural to couple another finite volume type of model to MPAS-Ol. That's the motivation for developing this type of model. But we can couple both models to MPAS-Ol, so we can do research. We can do some comparisons between the two models going forward. So it's open.
Okay,
Joseph Zhang, Phil Wolfram here. Quick question for you related to this point. So I'm a little confused because when you come and visited with us, I don't know, maybe 2.5 years ago now, or 2 years ago, whatever it was, my understanding was the reason that we need something like MPAS-Ol was twofold. First of all, there's some process physics that MPAS-Ol isn't resolving in the coastal domain, and it's vanilla flavor. first of all, and second of all, SCHISM, when you bring it out to the coastal ocean, isn't able to respect geostrophic balance, which is really the key innovation of Todd's method with, you know, Trisk and the Thoburn paper, is that you're able to get a finite volume discretization that you'd use in an estuary, but you're able to actually respect geostrophic balance and have all these conservation properties. I might be missing something here, but I think I didn't really see that in the discussion. Can you maybe just comment on that?
Yeah, yes, that's a good point. Yes, yeah, we in developing MPAS-Ol, we tried as much as possible to conform to MPAS-Ol approach, the Trisk approach. Although we did not strictly use that approach, but they, you know, they lots of algorithms were borrowed from MPAS-Ol. So to have mass conservation, to improve the conservation for potential vorticity and energy, etc. But like I said, in the actual estuary and nearshore models, it didn't seem to be a top issue. And on the other hand, the SCHISM, although does not strictly conserve the energy and the potential vorticity, the geostrophic balance is actually pretty good. We did lots of tests. I mean, it's I understand what you mean by you know, it definitely has a geostrophic mode, but you know, there are filters with which you can remove those modes. That's what we use for SCHISM. Yeah, but if you want a strict conservation, especially wetting and drying, conservation wetting and drying, which is very unique in MPAS-Ol, I would say MPAS-Ol has advantage.
But that comes at the cost of what appeared, and maybe we could go back to the slides just so that we're really clear on what we're looking at. I think that'd be helpful. It appeared that you needed some nonlinear iterations to do that. And yep. One of the strategies that we've always followed in MPAS-O, which, you know, coming from the coastal community as a suntans developer, which is also a derivative of untrim, you know, one of the strategies we always wanted to employ was using implicit methods and avoid iteration. And then coming to MPAS, because we're headed toward exascale computing, everything's been explicit so we scale properly, which has been really hard to do with implicit methods in the coastal community, to the point where codes like suntans and you know, selfie, we had some Jesse Mark, I'm trying to remember his last name, Lopez. You know, he spent a lot of time at Argonne getting, I think, Petsy moved into selfie to get some scaling, but it still rolls over at large processor count. So I think we have pretty substantial evidence that, you know, in the long run, explicit methods are really convenient and easy to get scaling. And when we talked about wetting and drying and actually using implicit, or not implicit, but iterations to resolve it, and maybe I've misunderstood something here. I guess I'm a little confused as to why we're doing that, because it seems like we're going to break scalability.
Yes, to some extent, but don't forget estuary systems are much smaller than a global grid, right? So you don't need lots of cores. That's the bottom line. And the advantage of using implicit methods is that you can resolve to depth. Okay, so that's theoretically doable with explicit model, but in practice, you know, there are lots of evidence supporting that. In practice, it's actually going to cause lots of stability issues.
So like ROMS, for instance, and Princeton Ocean model, which is, you know, not too different than the formulation of MPAS, they use explicit wetting and drying methods. So maybe you could just clarify some of the distinctions here as you see them. Like,
well, my understanding is wetting and drying algorithm is quite standard, and they definitely require reducing the time step if you want to do a good job in terms of wetting and drying. But the advantage of this type of nonlinear solver is that you don't have to reduce the time step. And like I said, the grid size is much smaller than global ocean, even with very high resolution. So stability is definitely not as good as the explicit model, but in terms of actual efficiency, I would argue it's better, especially when you go to high resolution. You know what I mean? Scalability is not the same as efficiency.
So let me interrupt this, because I think we're kind of down into the details of some of the technical aspects of working with this in E3SM. Are there any kind of more high-level questions for Joseph, and then we can let people go and kind of move on to some of these, more of the details in terms of it being a good pathway for E3SM? Any more? So if there aren't, then, people who aren't interested